So today I want to talk about computing, specifically quantum computing, and that's because I think it's much simpler than it seems. The issue today is that there's so many pop sci articles out about it that just give you like this really glossed over like soundbite kind of description of it that it's misleading. It's not that it's like completely wrong. I just think it ends up being extremely misleading. I think part of the problem is like the journalist doesn't really understand it, and so they do their best, and they're just kind of lost by the person trying to explain it. And even among the PhDs, they still disagree on like certain facts of it. But I think you can extract kind of a core gut feeling for what it's good at, especially if you compare it to other forms of computing. So I'll show you a few different ways you can compute things. And the idea is that we will like progress up to try to like give you that gut feeling about what is quantum computing actually, and how it kind of compares to other computing. And that way you can, on your own, think about what would it be good at and what would it not be good at. So let's start with classical computing. All right. So classical computing comes from one fundamental truth of the universe, which is cause and effect. We live in a cause and effect universe. Everything is built on top of cause and effect. So you're like, even gravity? It's like, yes, even gravity abides by cause and effect. Even quantum mechanics abides by cause and effect. Everything we know has like a cause and then an effect that happens after. That explains the progression of time, everything. And so even back in the day, like all the old math like Euclid and the ancient Greeks, the reason all that stuff is still true is because they made a very, very basic assumption. They said, we have to boil things down to statements. Statements are something that's either unambiguously true or false. And that's such a core assumption about our universe that has proven to be extremely durable and extremely useful. And so what that actually looks like is like there's too many problems to describe, but like this works for almost anything you do in your daily life that like I couldn't tell you what kind of problem is good for. You really have to think of things it's bad at. Like let's say you're driving to the store and you're like, okay, if traffic's bad, then I'll go to this other store. It's literally as simple as, if this thing ends up being true, then I'll do this other thing. So really just think of it as this, like if one, if true, 1, 0, however you want to think about it. If true, then do this other thing. And so you can think of like, we've heard of bits, ones and zeros, Boolean logic, binary. These are all ways of saying we're encoding two states, a true state and a false state. And if we have to represent anything else, like lots of life kind of happens on a spectrum, right? How do you represent that with cause and effect with classical computing? You just use more bits. Every bit you add to describe something doubles the amount of possibilities you can describe. It's like 20 questions, like 20 questions. Once you've got through the game of 20 questions, you can describe hyper-specific things. And every question you add past 20 just gets more and more specific, exponentially increasing the amount of things you can describe via 20 questions. So as a classical computer like programmer, what you're really thinking of is like these if-thens. You're not thinking of like a bunch of ones and zeros. Oh, I got to flip the second zero and then I move to the seventh one and turn that to a 1 or whatever. You're really thinking, you're using your cause and effect brain, which everyone does every day already. And you're saying, how can I combine all these if statements? If this is true, then do this. But if this is true, then do that. And that's all classical computing is. That's how come you see classical computers built all sorts of ways. Like back in the day, they were built with like wood and iron. And nowadays they're electrical circuits because it's just easier, just microscopic electrical circuits to say, if the current's running here, that's a true. If it's not running there, then that's a false, right? But that explains why you can build like calculators and stuff in like Minecraft or Little Big Planet, or I don't know the specifics, but like, people are able to build computing machines and games. It's just, less convenient than using an electrical circuit, but certainly possible. And that's because it's premised on cause and effect, which underlies everything in our universe. All right, so let's move on to a higher level form of computing. I'm going to call this like water computing because it's really silly. Okay, so water computing uses things like gravity and, fluid dynamics and friction and, all that stuff, fluids, right? And this was a popular problem, I think, a few years ago. It is a really fun thing. I know Stephen Mould covered it, and a really great quantum computing channel named Lucas Lab used it as an example, but I'm going to use it for like in a different case here. So the way it works is imagine you have a maze like this with like an exterior entrance and an exterior exit, and it's like, vertical, right? And it's like, made out of plastic, like a bunch of little plastic walls, right? To like make some maze, I don't know, right? So you have some funny maze like this, and you dump water in the top, right? Water splashing in the top, and it goes through this maze and it finds a path out, right? So this was a very popular way of saying like water can solve a maze. And what's really happening is like the combination of gravity pulling the fluid down and like the friction and the electromagnetic interaction between, the walls of the maze and the fluid, it ends up finding a path through the maze that kind of solves a maze for you, right? And so in a way you could think that like water and gravity have kind of encoded this problem in them. Like nature has somehow given us the answer to solving a maze by just dumping water in a maze. We don't think of like using water to solve a maze as a bunch of if-then statements. We're not thinking about every little particle. It's like nature does that for us. By using a higher level, fact of the universe, we gain some things, but it also makes some things more complicated. Like if we wanted to implement a classical computer with water, we'd have to like make gates, like, water gates that hold the water back. And like when they're open, it's true. When they're closed, it's a false. It'd be kind of cumbersome to do that, right? But in the case of solving mazes, it actually is very advantageous because nature, through gravity and fluid dynamics and all that, has kind of solved the problem for us. So we kind of get it for free in a way, right? So it's not like a water computer is superior to a classical computer because you could make gates that do classical computing, but you can also solve these mazes. The reality is that a water maze would probably be pretty bad at classical computing, but it's very good at this one problem of solving like a maze. All right. So let's move on to quantum computing now. Quantum computing, hopefully you see where I'm going. It's very similar, but instead of using gravity, it uses things like waves and superposition and then entanglement. These are all quantum mechanical effects, right? So it's using, again, like a higher level fact of the universe. It's like built on top of cause and effect, right? So just like with a water computer, it comes with some trade-offs. A quantum computer has a lot more crap going on that would make making a classical computer out of it kind of inconvenient. You probably wouldn't want to use a quantum computer for making a classical computer. There's lots of drawbacks to these effects, just like water and gravity. But these effects combined, right, they actually give us something that's useful. And so these effects, as described in Schrodinger's equation, there's something that they give us, and it's called an eigenvalue. The core fact of a quantum computing is Schrodinger's equation, and eigenvalues are a core part of that. Basically, it's like we like to think of the universe as being like infinitely like variable. Like if only you zoom in more, there's more detail to discover. Like you can always like kind of infinitely turn the knob in smaller and smaller increments. But like that's not true in quantum mechanics. Like these quantum particles have properties like energy or momentum, and those come in discrete steps. And those discrete steps are described by like eigenvalues. So it's like nature has encoded these eigenvalues for us, the same way it's kind of encoded this maze problem. So if eigenvalues were useful for us to know, then like nature has them in there. Like another way to think about it too is like, you have like an atom with like a nucleus and electrons around it. Like every level, like those electrons are never just in random spots. They're always at like these discrete orbitals, and you could think of like every orbital as being like a different eigenvalue that they kind of snap to. So it's literally part of the universe. And on top of all that, it turns out eigenvalues are useful. Normally, if you were to compute an eigenvalue using like classical computing, you'd have to take all your data. It'd be like in the form of a matrix, like rows and columns, and you'd like take every row times every column, every row times every column, multiply all these numbers together, add them up, and after all those steps, the bigger your matrix is, the longer it takes. But with quantum computing, the eigenvalue is in nature. If only we could read that eigenvalue in some way, we would have the answer effectively instantly, right? It would be much more efficient. And so quantum algorithms, like literally every notable quantum algorithm, relies on somehow reading eigenvalues to derive meaning, right? Sometimes, like in one case, you use eigenvalues to like have a opposite eigenvalue. So if everything's positive and your one thing is negative, you can boost that signal to like give you the answer, right? It's kind of contrived, but like that's something you could do. Or in another algorithm, like a very famous algorithm called Shor's algorithm, the key part is actually reading out the eigenvalue, not just detecting like, oh, here's a negative one, but actually reading out an integer value for that eigenvalue. Because if you have a really hard math problem that can be solved with an eigenvalue, you can save a lot of time if a quantum computer could just give you that number precisely. And that's actually the killer app for quantum computing is eigenvalues, right? Is like Shor's algorithm that breaks certain kinds of cryptography. What it's really doing is it's saying, if only I had this eigenvalue, I could solve these really hard math problems. And people just discovered a very clever way of actually reading out the precise eigenvalue. And so let me explain just briefly why that is, right? So here's the issue with like the popular science explanations where like you lose that gut feeling for like how eigenvalues are really what you want. And those are like this natural byproduct of quantum mechanics and Schrodinger's equation. This is where they fail, is that like they'll say things that are very misleading, like, oh, it's like classical meaning ones and zeros, but sometimes you have a 1 and a 0 at the same time. So that's not quite right. You really have something that's between a 1 and a 0. So a quantum particle you can really think of as a sphere, and you can pick any point in that sphere. You're not limited just like the North Pole or the South Pole. You can pick any point. So let's say the North Pole is a 0 and the South Pole is a 1. You can pick any other point. So if you pick a point on the equator, that's like halfway between a 0 and a 1, right? It's not necessarily both at once. That's kind of like misleading, right? And also, how would it help you if you have a string of zeros and ones and then you decide to insert this arbitrary thing that's between a 0 and a 1? How does it help you compute anything, right? You still need an if-then, right? But how do you write like an if-then when it's between a 0 and a 1? And if quantum computing, when you have a qubit, the quantum equivalent of a bit, when you have it in the state that's between a 0 and a 1, it will randomly collapse to a 0 or a 1. So you've effectively just made a random algorithm. Like that doesn't actually help you compute anything. What this helps you do though, right, is if you think of a qubit as a sphere, imagine that you don't change the orientation of that sphere between 0 and 1. So like the North Pole, imagine you don't rotate. So the North Pole is still at 0 at the top, and the South Pole is still at 1 at the bottom, right? But imagine you rotate it along that axis, kind of like how our planet spins along the axis, right? That's what we would call the phase. And that phase is basically the eigenvalue, right? So just seeing those being kind of like synonymous terms, right? And so the problem with the quantum computer, though, is that we can't actually read that phase precisely. We have to like tease it out. We either have to have very simple phases that we can tease out easily, or we have to use something like Shor's algorithm with quantum phase estimation that kind of reads out that phase as an integer, right? And so hopefully that kind of elucidates some things about it. Is like, there's not like a guy who has like these tiny instruments who's like saying, time to put that in superposition, time to entangle that. Those are laws of the universe that you like have to work around in a sense. Like you wouldn't be able to take the exact same algorithm and say, okay, do the same thing but without entanglement. You couldn't make your water maze and say, okay, let's do the same thing but without gravity, right? These are forces of nature that lead to these eigenvalues falling out, right? So it's up to us. Like a quantum computer scientist will actually think of it this way. He will say, okay, I have all these qubits, right? And if I prepare them in this certain state, right, and I put them through this gate does some math for me, like, adds two numbers. So I input these qubits, right, and then I get this output. Now the funny thing is, it's like if you set up your quantum circuit a certain way, you can actually read the phase of the qubits, right? You actually don't really care about this answer that comes out the other end. You just care about like, how did the phase change? When I added these numbers, how did the phase change? Because that phase is telling me something separate. I'm actually not interested in adding numbers. I'm interested in a different property of this problem. I don't care that 2 + 5 = 7. I actually care about like what the relationship is between 2 and 5, which gets encoded in this eigenvalue that falls out, right? So hopefully that kind of makes sense, where like what you're really doing is like a quantum computer scientist is thinking of like operations and gates and saying, how can I get these eigenvalues? How can I extract some meaning from these eigenvalues? Right? It's not really about saying, let me arbitrarily change some ones and zeros to a superposition of a 1 0, or let me arbitrarily start entangling them. All that happens automatically, whether you like it or not. It's a law of the universe. You're not really controlling that individually. You're really thinking about operations, and you're saying quantum computing has more information in it, and some of that information is like encoded in the universe that might be useful, specifically eigenvalues. They're part of the universe. Is there a way that I can leverage these eigenvalues, this extra information I get from my operation? So you're really thinking, just like a water computer scientist thinking about like gravity and fluids. As a quantum computer scientist, you're really thinking about gates and eigenvalues and phases, and you're saying how can these things tell me something about the problem that I would otherwise have to compute with a bunch of ones and zeros in a very cumbersome way, right? And that's a very hard problem, right? So Shor's algorithm, quantum phase estimation, to actually read out an eigenvalue, kind of like the killer app, the pinnacle of quantum computing, that was discovered in like 94, 95. That's how hard it is to think of quantum computer like algorithms. Is like, that's like the pinnacle in some sense, and that is already like 30 years old now. It's a very hard field because it boils down to how we can cleverly use eigenvalues. How can we cleverly get eigenvalues from nature to solve problems for us? So yeah, hopefully that made things less confusing in some way, or hopefully at least demonstrate what is the actual power of quantum computing versus what you've read in pop sci articles about entangling qubits and a 0 and a 1. And so if you liked it, please comment. I'll leave some descriptions. Like I said, Stephen Mould has a video on the maze, and Lucas Lab is a great quantum computing channel. And so I'll leave some links to some channels I like too that I think do a much better job of explaining all this. But yeah, please comment. Let me know if I made any mistakes or if you have any, feedback, and like and subscribe and all that. Thanks for watching.